All right, time to review some derivatives for the Unit 3 test. So here we go. First type of questions we're going to be looking at here are these ones where we're finding all these good old features about these graphs, okay? So we want to find critical points, extrema, increasing, decreasing, all that good stuff. So we're going to need the derivative. Let's find the derivative here. And so there we got our derivative, f prime. And let's go ahead and get a number line for that thing. And, well, we're going to need to find out where it's equal to 0. So we can set it equal to 0. X squared plus 2x. All right, and I think this thing factors. That's nice. X plus 4 and x minus 2, right? And so our zeros are at x equals -4 and 2. So -4 and 2. So we found our critical values here. And so we've got critical values at x equals -4 and 2. Okay, coming from the first derivative. Okay, and so let's come on over here and let's plug in values. We can plug in like -5, and -5 is going to come out to be a negative times a negative, which will give us a positive, and so that's going to be increasing. We have something in between like 0. Plug in 0 into the derivative, and we get 4 times -2, that's a negative, okay? And plug in something like +3, and we get 7 positive, so that's going to be positive, okay? So we're increasing, we're decreasing, and we're increasing, right? So that means we've got some extrema. We're going to have right here, we're going to have a maximum. So we have a max at x equals -4. And we have a min at x equals 2. We don't care about the y values right now, just those are our x values. Increasing, well, we got increasing in these two intervals here. So that's going to give us from -infinity to -4, and also from 2 to infinity. All right, we're going to put a little union there. And the intervals of decreasing, well, that's going to be from -4 to 2. That's where the first derivative is 0. So inflection points now, to find some inflection points, we're going to need to find the second derivative. So let's come on over here. Here's our first derivative. We'll take the second derivative of that now. And let's go on over here. Polynomial makes a nice quick derivative. Now let's set it equal to 0 and solve it. And so we can subtract 2 divided by 2, and we get -1. All right. So we're making our number line. We can get our critical values there. And we know that when x is -1, somewhere on the line, we have a critical value. To the left, these are numbers like -2. So if we plug in -2, we get 2 times -2 plus 2. That's going to be negative, right? And if we plug in a number to the right, like 0, well, we're going to get a positive value, okay? And -1 will give us 0. So this is concave down, and this is concave up, all right? So that's our concavity. So we can come over here. We do have an inflection point because it changes. Inflection point is at x equals -1. Interval is concave up is going to be from -1 to infinity. Concave down would be from -infinity to -1. All right. And there you have it. Okay. There's a polynomial. Not too shabby. Should be pretty quick to do that. Now let's go ahead and try a rational function here. All right. Let's find those key features for a rational function. When you're doing a rational function, it's definitely helpful to be thinking of the graph. All right. The polynomial, you can think of the graph too. You think of the end behavior and some things we know there. Here we had a third degree. So looking at the graph here, we know it's third degree. And it's a positive leading coefficient. So, we're probably looking at something like this. Okay? And so that matches our increasing, decreasing, and so on and so forth. So keep in mind on the graph. All right? So here we go. Key features here. Well, the denominator here factors into x plus 1, x minus 1. And so it's undefined at -1 and +1. All right, so it's undefined. We're going to have some asymptotes there. Rational function, we kind of expect that. Okay, now we want to think about any horizontal asymptotes. And so we remember from pre-calculus there, if the degree is bigger on the bottom than the top, then it's going to 0. Okay, and the reason is if you find the limit, let's talk calculus here, if we find the limit as x goes to infinity, either plus or minus infinity, okay, of 2x minus 4 over x squared minus 1, okay, it's infinity over infinity right now, and so we could use L'Hopital's rule, and using L'Hopital's rule, we see that, let's get this stuff out of the way. Taking the derivative of the top and the bottom, it's a pretty quick deal. We can see this is going to 0. Okay, took the derivative here, 2, took the derivative here, 2x. That's L'Hopital's rule, all right? You can also just pretty much see, bigger degree on the bottom, it's going to 0. This is, x squared is a lot bigger than the x, okay? Anyways, L'Hopital's rule, if you know it, there you go. So you guys should know that there. Okay, so it's going to 0, so we know as we go to infinity, that is going to 0. Good to know. All right, some critical points. Let's find some derivatives. Let's find f prime. We're going to take that derivative of the top times the bottom and minus the top times the derivative of the bottom. Moving over a bit here. And we have the bottom squared. All right. The top will clean up here. And so we end up with polynomial like this, -2x squared. That comes from multiplying these and multiplying these two x's and then negative. And you'll get that. Clean it all up, you get that. All right. So that's all over x squared minus 1 squared. No need to multiply that out, so let's leave that alone there, right? And so now we want to set this equal to 0 to find the critical values, and all that matters is the numerator, right? Okay, we notice that x cannot be 1 or -1, so we already have that. That's the asymptotes, okay? So those are critical values. Let's see, x equals plus or minus 1. So we got to put those down because it's undefined. But setting the top equal to 0, let's go like this. And we'll factor it while we're at it. Pull out a -2. And we have x squared minus 4x plus 1. All right, setting that equal to 0. You can divide off the -2, and all we care about is the inside equals 0. And that does not factor, so we'll have to use some quadratic formula. So we get 2 plus or minus the square root of 3 when we use a quadratic formula. We can also just go ahead and use our calculator, and this would be a calculator problem. And so we'll pull in our little calculator here, and we see we have, if we solve this, we get the same thing we just said there. A little different form because the calculator likes it in different form, but we get that's 0.27 and 3.73. How about that? Okay, 0.27, 3.73. All right, so put that away. And we said 0.27. Put that on a number line. So we got that on our number line, and we also have our other critical values of -1 and 1. And we're going to test that out now. This is f of x, prime of x, that is. And so we're going to test that out with our derivative to find our increasing and decreasing. So we're going to plug these in here. If we plug in some of these values, we're going to get something like this. If we plug in -2, we're going to get a negative on top. The bottom's always positive. If we plug in 0, we get negative on top. The bottom was always positive. That gives us negative. If we plug in 0.5, 0.5 is between here, that gives us 4 minus 2, which is 2. Plug in 0.5 here, we get something less than -2. So this will come out to be positive, all right? So 0.5 is going to give us positive. Then we can plug in something like 2. Okay, so 2 is going to give us -8. It's going to give us plus 16 minus 2. And that whole thing is going to be positive. Plug in something like 4. When we get 4 here, we're going to get 16 negative 32 plus plus 32 minus 2. So that's going to be a negative. Again, the bottom's always positive. So there's our increasing and our decreasing. We know that our negative, our negative 1 and our 1, those are going to be asymptotes there, okay? And this guy is going to be going down, going to be going up here. So there's going to be a minimum there. And this one's going to be going up because it's positive, and down. So that makes this a max. So let's get that information in here. Going back to our critical values and our extrema, we can get those. And we get these guys. Okay, our intervals of increasing and decreasing. Let's get those. We just said these down here. We'll copy those from this right here. And there we go. We got our intervals of increasing. Those are our positive first derivative. Intervals of decreasing. That's our negative first derivative. Inflection points and concave up. That's our second derivative. So let's get into that real quickly. So let's come over here looking at our first derivative right here. Okay. And let's use the quotient rule yet again. All right. So using the quotient rule for this guy. Derivative of the top, we get -4x plus 8 times the bottom, x minus 1 squared. Then we're going to get the top. Let's see, we need to move this. Then our second parts, we have, we got a minus here. Minus the top, which is that big old ugly thing, times the derivative of the bottom, a little chain rule, derivative of the inside, 2x, times the derivative of the whole thing down here, drop the 2 down, and x squared minus 1, all over the bottom squared. Okay, let's go ahead and clean this mess up. So we can pull out an x squared minus 1 because it's there and there. We can pull out a 2. I'm going to pull a 2 out of there, leaving us with a negative 2x plus 4. And then this 2 gets pulled out. This thing got pulled out, and one of these got pulled out, leaving half of this, and one of these guys, leaving this thing here, and almost forgot the 2x. All right, let's go ahead and cancel that, maybe with one of those, so I don't have to write as much. This is getting ugly. And clean up the inside. It looks something like this. Just noticed something that you probably noticed a long time ago if you're paying attention, if you're awake. I'm not awake. I don't know where that squared came from. That was just a plain old 8x. So distributing that through and multiplying that out, we get these guys here. And let's finish it off by just combining these crazy things. Don't leave behind that denominator there. All right, and we get a positive 2x cubed. We get a negative 12. We get a 2x minus negative 4x. Oh, that's going to be a 6x. And we have a negative 4. Okay, all over this x squared minus 1 cubed. Okay, now we want to find our critical values, so let's set that equal to 0. Okay, and so all we care about there is what makes the top 0. Let's go to our calculator. Don't try to mess with that. Go solve that thing in your calculator. So pulling this in from our calculator, we get 5.52. All right, so 5.52. All right, let's tuck that guy away. That's good to know. So 5.52. Only one answer. 5.52. All right. So our critical points for the second derivative number line are still negative 1 and 1. Because that makes a denominator 0, and then 5.52. Obviously not drawn to scale here. We're not worried about that. Our number line is just so we can test some things out, okay? So let's go ahead and test it out real quickly. Looking at this big ugly guy, plug in like negative 2. Negative 2, that's going to give us a positive on the bottom. That's good to know. Okay, negative 2 in this big old thing gives us a negative. This whole thing will be negative, like 24. This will be a minus 12. Minus, everything's minus. So minus, minus, minus on the top, so that's negative. Okay, plug in 0. Oh, we like 0. Zero's in between here. And the top will be negative. So zeros, negative 4. On the bottom will be a negative. So the top was negative because it'll be negative 4 times 2. The bottom will be negative because it's negative 1 cubed. So negative over negative, positive. All right, plug in something in between here. Let's try positive 2. All right, positive 2 is going to give us 4 times negative. That's negative 48. This is going to be a positive 16. This is going to be a positive 12. And negative 48 is bigger than 16 and 12 put together. So that's going to make this negative. This thing inside is going to be negative. Okay, plug into here. And this is going to be a positive number. We'll get negative over positive. And so we have negative. And then plug in something like 6. Okay, 6. Bottom's going to be positive. We're going to get, 6 cubed is 216 times 2 is 2 times 216. Hey, this is 6 squared. Oh, notice this. This is 2 times 6 right here. So this is really 2 times 6 times 6 times 6. This is exactly the same as that. Those cancel each other out. That helps to know some factoring, okay? 2 times 6 times 6 times 6. That's the same amount as that. Whatever the number is, I don't care. They cross out. 6 times 6 is 36. Hey, this whole thing is going to be positive. So we said positive over negative. And so this is going to be negative. Wait a minute. I said positive here. And this is going to be positive. So positive over positive. That's positive. Okay. Whew, I think we got it. All right. So let's go ahead and get this in here. We've got an inflection point, and that's at 5.52. And we got intervals of concave up, and that's from -1 to 1. and then from 5.52 to infinity, okay? And so, what does this mean after all this craziness? Well, we've got this. Let's look at our graph here, okay? Over here, we know we got these asymptotes. We know we have a minimum at 0.27. If I find an y-intercept, plug in 0, I get -4 over -1. That's up here at 4 somewhere, wherever that's at, okay? And then I know at 0.27, right about over here. Okay, let's zoom in a bit here. At 0.27, we get a minimum, and we know we are concave up in the middle. So we got to go down to a minimum, and then we're going up. And then we're going up from there, okay? And then we know, what else do we know here? We have a maximum at 3.73. We got an inflection point, okay? And we are increasing from 1 to 3.73. So we've got a maximum somewhere over here at 3.73. We're increasing, okay? And then we're going to come around here. We're concave down. We have an inflection point at about 5.52, okay? So at 5.52, it's gonna flatten out, because as we go to infinity here, this whole thing is going to 0. Going to infinity, this going to 0 because the bottom's bigger than the top, okay? And then, so we got an inflection point, we got a maximum. Over on this side, we don't have a maximum at all. It is decreasing from -infinity to -1, right? And we also know that it's going to 0. When we go to -infinity, this thing's going to 0. So it's decreasing, and it's going to 0. So it's got to be looking like that. Okay? There's our crazy-looking graph, all right? Now, that wasn't asked for there, but the sketch helps clear that up a little bit. Okay? And so go to your graph, and believe it or not, we'll get something that looks like that. All right? So great job. That was a big one, okay? And we want to use our calculator in here on this stuff to solve these things. I suppose we could have even used our calculator to simplify this, take the derivative of that. But there you have it, okay? Hang in there. You're getting it. You should be proud if you made it through that thing. All right, let's look at some situations where we are going to have a graph and we want to find some important values, all right? So here we have a graph of f of x, so just the graph itself, all right? What are the critical points? Remember, critical points are where it's undefined and where we have minimums and maximums. So that's at x equals 0 and b and E, all right? Those are our mins and our maxes, okay? And so those are the extrema there, all right? So same points, all right? We could have points where we had undefined. That would be a critical point and not an extrema, but not in this situation. Intervals of increasing, well, we're going up to the right from 0 to b, and from E to infinity. All right, that's this guy right here. Okay, increasing. Decreasing is on these sections right here. And so that's going to be at negative infinity to 0 and B to E. All right, so going downhill. Inflection points. So those are points where it changes from concave up like a cup, to concave down like a frown. And so right in here, it looks like it's changing, and I'm thinking that that's at A. And here it's down like a frown, but all of a sudden it's up like a cup. So right in here, oh, that's kind of a tricky one. I'm going to actually guess it's D, and it is D. So That's what we want. Okay. Whoops. That is going to go right here. All right. Concave up like a cup. Well, that goes from negative infinity to A. So because it's up right here. And then it's also up right here. D, we said, was our inflection point. That's what we decided. So from D to infinity, it's also up like a cup there, all right? Down like a frown. Well, that's from A to D. From here to there. That's concave down, all right? And that's it. All right, so that's just looking at the graph and understanding what those terms mean, right? All right, so now we have the first derivative, okay? So first derivative, we got to be careful here and think carefully about these. When we have critical points, well, that happens where the first derivative, f prime of x, is 0, all right? So looking at the graph, where is f prime of x equal to 0 or undefined? F prime of x is 0 at x equals 0, b, and e. By the way, these two graphs have nothing to do with each other, so don't get confused there. Maybe it would be a good idea for us to use a g of x or something like that, but we didn't. Oh well. Extrema, all right? So extrema happen when we have a critical point, first of all, but also what needs to happen is the derivative needs to change. So we have this. What's helpful here is if we take this and we translate this into a number line for f prime of x. And we know that all the way up to the value of c, the derivative is positive because we're above the graph over here. And then we're below the graph, so the derivative is negative from c to f. And then we're above the graph over to the right, so that is positive. Okay? So now, looking at this here, we can see where does the derivative actually change? Well, we have it's going up, we're increasing. The function f of x will be increasing to c and then decreasing after c, all right? So c is going to be a max. Max at x equals c, and we have a minimum at x equals f. Point f, that is. All right. All right, so that's a key. So this 0 here is not an extrema in this case, all right? Because the derivative, the sign of the derivative does not change. Now, intervals of increasing and decreasing. Let's see here. We're increasing. Let's use our number line. So we're increasing from negative infinity to c, and then we're increasing from f to infinity. Where are we decreasing? That's when the derivative is negative, and so we're decreasing from c to f. Okay. Where's our inflection points? All right, so now we got to think second derivative. Second derivative comes from the slope, so let's make a number line here for the second derivative. The second derivative is the slope of the first derivative, all right? So we can say this, our slope up to the point 0 is negative. Then our slope is positive, going to b. And then the slope is negative, going down to e there. All right, going to e. And then from e to infinity, we're going up. Okay, the slope of the first derivative is the second derivative. So this little chart here, this little number line can be super helpful, all right? So with that now, let's just even ignore the graph, and we can see inflection points. That's where concavity changes. That's going to happen at 0. That's going to happen at B, and that's going to happen at E. All right? Where are we concave up? Well, we're concave up whenever the second derivative is positive. Okay? So that comes from 0 to B and E to infinity. Okay? And let's move this jazz. Concave down, looking at our, let's see here. The concave down is where we're negative, looking at our sine graph there. And so that's from negative infinity to 0 and from B to E. All right? So next, last but not least, let's sketch a graph using these derivative features, okay? So we know we have a max at C, somewhere at C we'll have a max. We have a minimum at F, all right? We don't know exactly where, but we just know it's a minimum. Now, this was not given a start value, so if we had a start value, then that'd be great. We might assume that f of 0 is 0, but that's not necessarily true, all right? But we need some kind of start value, so we'll make that up because it wasn't given to us. You just pick one if it's not given to you. We know we're increasing, so we're going to go increasing, and so let's see. So we're increasing, but we are concave down to 0. All right. So we're increasing, concave down. There we go. Okay. Increasing as we go to the right. Then what happens at 0 to B? Notice we're still increasing from 0 to B, but now we are concave up like a cup. All right. So we're concave up. Then from, we have it here at C. Okay, C, we know we have a maximum, all right? And we're now concave down, all right? So I guess I should move this maximum the way my graph is going. So we got an inflection point at B. So our concavity changes, all right? We're going up to our maximum. Okay, C is a maximum. Now we're at C. Let's continue on. Let's go to D. Anything happening at D? Nothing's happening at D. Next place that something happens is at E. So going from B to E, we have, we're concave down. Okay, like this is concave down. And we are decreasing from C going towards E. So we're decreasing, concave down. And then from E to F, we know we're decreasing. And we are concave up because everything after E is concave up. So we'll need to be concave up like a cup. And then we're concave up and increasing because here we're increasing, F prime is positive, and we're concave up. Okay, there's a graph, something along that line. Again, this whole thing could move vertically or horizontally because we don't know the starting point, but that's a good place to start, to assume. All right, so there's a couple problems going from a graph to the information, all right, the special values. So here we got a function P of t that represents a population of fruit flies in the container at time t. And so we want to describe what's going on here, okay? And so here we have some descriptions. Well, these are all F's. Let's call this F, all right? So what's going on here, all right? We have first derivative is positive, and the second derivative is positive. So that means a little picture can be a big helpful. We're increasing, concave up. Here we have first derivative is less, so we're decreasing, and we're concave up, all right? So here we're decreasing, concave up. For this guy, we are increasing, concave down. So increasing, concave down. For this guy, we are decreasing, and we are concave down. So we're decreasing, concave down. There's our 4 possibilities. So what does this mean? So here, our population is increasing, okay? And we might say that it's at quicker rates, okay? So the population is increasing and the rate of increasing is getting larger. Well, here, population is decreasing, all right? So the population is decreasing, and the amount that it's decreasing is shrinking. So, okay, so we might say the population is decreasing by less each day. So, less and less. How about that? Fancy way to say it, huh? As time increases. All right? Okay? So now we have what's happening here. We're increasing, but we're not increasing as fast. So the population is increasing, but the amount of its increase, or the rate, is getting less, okay? By a smaller rate. Okay. As time goes on, all right? And so what's happening here? Here our population is decreasing because the function's going down. And the rate that we're decreasing is getting faster. Here, we're not decreasing very much. Now we're decreasing a little more, and now it's just dropping fast, okay? So we can say by more as time increases. All right? So let's keep it kind of the same. Okay? As time increases. So that's kind of the idea, all right? So it's increasing, decreasing, but the rate at which it increases or decreases is changing as well, all right? Okay, we're going to move on to a little mean value theorem here as we look at some more applications. Okay, so here we want to know, does the mean value theorem apply on the interval given? And if so, what is the value that's guaranteed? All right, so 2 parts there. So the first part here is does the mean value, the hypothesis of the mean value theorem apply here? 2 hypotheses. Is it differentiable? And is it continuous? All right, so this is a rational function. So we know on this rational function, x cannot be -3. And is -3 on this interval? It sure is. So there's a break on this graph in that interval. So we can say MVT does not hold or not apply because it's not not continuous. It's got to be continuous and differentiable. So it's not continuous on the interval here. Whoops, come back. Okay. All right, that's the idea there. How about this one? Well, it's another irrational function. We know x cannot be 1. Is 1 on this interval? Nope, it's not. So that's not a concern, so we can go ahead and find the derivative, okay? So first thing here, let's find our secant line. Delta y, delta x, and so that would be f of 4 minus f of 2 all over 4 minus 2. F of 4 gives us 1/3, and f of 2 gives us 1 over 1. And 4 minus 2 is obviously 2. So this is going to be 1/3 minus 1 all over 2. Let's multiply top and bottom by 3. How about? We can just a couple ways, but let's go like this, okay? So that would change it to 1 minus 3 as you distribute this little guy all over 6. And that's going to give us negative 2/6, which is negative 1/3. Okay, so that's our secant value, the slope of the secant line. And so now we've got to find the derivative of f. All right, and so we can think of this as x minus 1. You can use the quotient rule, or you can think of this as f of x equals x minus 1 to negative 1. I'm going to try that value that way. Using the chain rule here, derivative of the inside is just 1. And then times the derivative of the outside, the whole, which is negative 1, times x minus 2 to the negative 2. All right, so that's simply negative 1 over x minus 2 squared. All right, we want that to be equal to negative 1/3, okay? So negative 1 over x minus 2 squared equals negative 1/3. We can do a little cross multiplying, okay? And so we have negative 3 equals negative x minus 2 squared. All right, I'm going to multiply both sides by negative 1. Let's just make this positive, in other words, okay? So 3 equals, and we have x squared. Oh, what are we doing? Don't multiply that out. So we want to get rid of the square there, so let's just square root both sides. Okay, and I made everything positive, so the square root doesn't matter there. Okay, so we have the square root of 3 plus or minus, and x minus 2, add 2 to both sides. X equals 2 plus or minus the square root of 3. All right, so there's our answers. What is that? That's approximately 0.27 and 3.7. All right, 7.3. Actually, let's put a couple decimals of accuracy. Okay, and looking back, which one of those are on this interval? Well, from 2 to 4, only the second one is. All right, so our solution for part 2 is x equals 3.73. Okay. So, and we should have said part 1 here. Yes, MVT applies. All right, there's our solutions for B. Okay, our solution for 1 says that it doesn't apply. So we don't need to do part 2. All right, cruising along here. C, we have 1/3. So this is a cube root here. All right, so a cube root's defined everywhere. So part 1, it is continuous and differentiable. So MVT applies. All right, it's everywhere differentiable. All right. So let's go ahead and find the derivative now. F prime of x is going to give us 1/3 x to the negative 2/3. Okay. Also known as 1 over 3x to the 2/3. Okay. Let's find our secant line. So our secant line, delta y over delta x, that's going to be f of 1, right? Yep. F of 1 minus f of negative 1 all over 1 minus negative 1. Okay? And the cube root of 1 is 1. Cube root of negative 1 is negative 1. All right? And so 1 minus negative 1. Hey, those look a lot alike. So this whole thing is just equal to 1. All right? So let's set our derivative equal to 1. So we have 1 over, let's get a different color here. 1 over 3x to the 2/3 equals 1. Cross multiply, we're just saying that 3x to the 2/3 equals 1. Okay, and so multiply by 3. So x to the 2/3 equals 1/3. So x is 1/3 to the 3/2 power. And let's go to our calculator for that. And we get about 0.19. And that would be plus or minus. Okay, because we took a square root there. When you square root, it's going to be plus or minus. All right, so the answer here is x equals 0.19 or negative 0.19. Two solutions there. All right, and one more here of this type. So here, this is an absolute value function. And we got to know a little bit about absolute value functions. It helps to know that the graph of this guy looks like this. It's a V, and I didn't do that very well. It's going to touch the axis right here at -4. All right, and at that point, it's differentiable. So for part 1, it's not differentiable at x equals -4. Okay. So since -4 is in this interval, MVT doesn't apply. Okay, it fails the test. All right, that's how we use mean value theorem. Let's turn our attention to some L'Hopital's rule here. Remember with L'Hopital's rule that it has to be equal to 0 over 0 or infinity over infinity. So when we plug in 2 here, this goes to 0 as it is. Okay, so plug in 2, and we get e to the 2 minus 2, which is 1 minus 1, which is 0. And the bottom goes to 0, so this is going to 0 over 0. So we can take the derivative, limit as x goes to 2, derivative of the top is a little chain rule. Derivative of the inside is 1. Derivative of e to the x minus 2 is e to the x minus 2. And the constant goes away. Derivative of the bottom is 2x. Now we try to plug this in. Does that work? Yep, we can plug this in. We get 4 on the bottom. And we get e to the 0 on top, which is 1. So 1/4 is our limit. And down here, we plug it in. We plug in infinity. We see that this goes to infinity over infinity. So L'Hopital's rule does apply. So let's take the derivative of the top, and that's 2x plus 2. Derivative of the bottom is just e to the x. If you plug in infinity there, you'll see that it's still going to infinity over infinity. So we got to take the derivative again. We get 2 on top and e to the x on the bottom. And now we have enough to see that yes, indeed, when we plug in infinity, all right, or a gigantic number, this is getting huge. So we have 2 over a huge number, and that is 0. And that's how we use L'Hopital's rule, all right? Remember, it's got to be going to 0 over 0, or infinity over infinity, or some negative or positive infinity combination. Now we're given some information about a graph f of x, given information about its derivatives here, and a little information, yeah, that's all we got. We don't have information much about f other than f of 0 and f of 3 is 0. So it looks like we've got 1, 2, 3, so we'll mark that on our graph. Get those points here. We can start by marking our zeros. Zeros happen at f of 0 when x is 0. And when f is 3, all right? That's good to know. We also know it's continuous, so some nice smooth curve going on here. Okay, so let's see what's going on. When the derivative is 0, that's a possible max and min, okay? Or if the derivative doesn't exist. If the derivative doesn't exist, that means we have a non-differential point, which usually means the graph is pointy, all right? So let's just start to sketch this out. we know that our derivative is positive for everything that's less than 1. All right? So less than 1, our derivative is positive. That means we're increasing. Okay, so we're going up. We're going up. At 1, looks like we have a maximum or possible maximum minimum. But what's happening? From 1 to 2, we're still going up. All right? And then from 2 to 3, we're going down. And then from 3 to infinity, we're going down. All right? So there's a general shape. Now let's talk concavity here. So what's going on? We got a negative, so we're concave down all the way up to 1. So we'll replace those with a curve. That's concave down. So we got concave down, and we're increasing. Now here the derivative is 0. And we notice that the second derivative is 0. Okay? That means it's a possible inflection point. All right? And it is because now we're going up, increasing, and we're concave up. So this guy here is going to go concave up, and it's increasing to 2. All right? Now, right here, we start to see a problem with the problem, all right? Because if from here, we're at some point at 2, and we've got to now go down, decreasing, and we've got to be concave up. No, I'm sorry, concave down. So we need to change directions, and it needs to go something like this. Okay? And so this, let me see. I'm going to change my height of these points real quick here. Okay. Same thing. I'm just going to drop this down a little bit so we can see this a little better. All right. So we're scooping up. And now we're scooping down, but what happens is we got a sharp point here. So there's a problem. This is the problem. These guys need to be D and E, do not exist. So all these factors don't go well together. That problem is messed up. All right, just right there. But anyways, we got our curve there. It's not differentiable at 2. That can't happen going from the positive to negative like that. Now, here we are going decreasing, but concave up. So that's our last bit there. So let's get rid of that. And we're going to go decreasing, concave up. So right here, this is a non-differentiable point. So that's why at 2, the derivatives don't exist. And here, the derivatives are 0. It's an inflection point, and it's a critical point. But remember, critical point doesn't mean it's a max or a min. All right, it could be an inflection point, and that's the case there, all right? Here's a good little problem, all right? We want to make a table so that, just make up some numbers so that f prime is greater than 0, and the second derivative is less than 0. So what does that mean? This means it's increasing. However, the rate at which it's increasing is shrinking, okay? So if it helps, a little graph here, this means we're increasing. This means concave down, all right? So because the second derivative is less than 0, so we're increasing by a lot, and then not quite as much, and then not quite as much, and not quite as much, all right? So 1 is whatever, some value, okay? 2 is bigger than 1 because we're increasing. 3 has got to be bigger than 2, but not as big of a jump. I don't know, let's call it 7. And now 4 has got to be bigger, but not quite as big of a jump. Let's call that 8. So the first derivative tells us that we're increasing. Okay, that's true. But the second derivative says we're increasing by not quite as much. 5 is our big first jump, and then we only jump by 2, and then we only jump by 1. Now, you can pick any numbers you want, but the difference in between them has to be shrinking. That's because the second derivative is less than 0. All right? We're kind of decelerating here.